If stuck is just a thing that we are throwing there. That's my timer, so I will be back in a few minutes. Alright, well, we're gonna get back to this. I've eaten my quick lunch. I didn't burn it. It's kind of hard to burn things when you boil them. But I'm sure Scorpion would be able to do it. So that's one thing that I was thinking about in the back of my mind was that little super jump thing. Basically, if you're running up a slope and you jump when you're running up the hill, you're going to actually jump higher because you had more initial velocity. And the question is that something that I should keep around? Because it's kind of interesting if you think about it. You boiled it dry and then burned it. Oh no. Because if you're running up a slope and then you jump, should you jump farther? I mean, in the real world, right, a person would be running up a slope and they're kind of already jumping, right? Just by pushing off of the ground. And when they actually jump at the end of it, you probably wouldn't get like a full jump. But if you were running up a ramp and then jumped, you'd probably, you'd go farther. Yeah, short movie, that's for sure. By movie, we meant YouTube video. Alright. So let's see. We cannot land. This is either because we're moving up or the surface is not landable. I think I'm going to leave that, running up a slope makes you go faster. It's kind of one of those little things that people might actually find and use to their advantage. Maybe they don't even know about it consciously. They just kind of figured out. They're like, oh man, look at that. I can jump higher if I run up this ramp. Nuts. So, let's apply friction, which is what we will do. It makes sense, no friction if we're not colliding with anything. So apply friction for hitting your head slash sliding on wall. Later, Scorp. Have a good one. So now we need to move along the wall. Slide along the wall or ceiling. So we need our calculator motion direction. And then this scope here just doesn't do anything, does it? So we need max ceiling travel iterations. Let's add that. Simple stuff, just chunk that off. Let's remove a lot of this debugging stuff, I don't need it anymore. So we're going to sweep our movement object, and if it's less than that, then we do this, otherwise we do this. So we're going to set ourselves to our end position. So basically, if we are actually finished moving here, so if our motion magnitude is less than this, well, why aren't we doing this check before? Why aren't we just saying, well, new motion magnitude is equal to tiny float? Then there's no reason to do anything. We just break out of the loop. We're done. Yeah, we're just like, and we are finished. So get out of it. Otherwise, we are setting ourselves to the position that we've just done, and then we're going to apply our friction, and our friction is going to be, it's extra delta t, because we didn't collide, so we're going to do the whole thing. This is what it looks like. So yeah, we didn't collide, so apply friction for the movement and set our position. And we got this friction code again. Yeah, we've got this friction code like 3 times, don't we? So we're probably going to want to do is make an apply friction function. If collision distance is less than tiny float. Not too difficult. So if our collision distance was less than a very small amount, then we set our position. So basically we either couldn't travel or we could travel. But we did collide, so we need to do all the rest of these checks. Alright, so we need to do like new velocity equals apply friction. We need to pass in Looks like a float delta t, and then a normal. Just like apply wall friction. And yeah, we're gonna need to pass in like new velocity. Actually, we shouldn't even have to pass in a velocity. We're just modifying the vector inline. So we're gonna pass in sub delta t. Looks like the collision impact normal is what we're doing. Alright, so let's make that function. Apply wall friction. I think what we did was F vector reference, that's going to be new velocity. We have a float delta t, and we've got a const F vector reference impact normal. So there's all of that. That should be just good to go. So there's our wall friction. Let's see, absolute value, C, -1, that all looks good. Slap this in our header function, our header stuff. So this one's going to be extra delta t. This one's going to be actual time simulated. And that looks actually pretty good. So let's go ahead and compile it, check it out, make sure it works. Actually, it looks like we need to do that as well. And we probably can combine everything right here with everything in the do while loop and have like a move in error function that steps and call itself with like a delta t nicely. So we don't have to have basically a copy paste of the exact same code where it moves itself. Alright. Function must return a value. Function should return it looks like it should return sub delta t. And we should be able to just get rid of sim time. problem? Let's double check that we're all actually working. Yeah, maybe we... Yeah, see, yeah, I think that jump is a little bit screwy. Like the, yeah. Because when you're running down the hill and you jump, like your jump sucks. You can't jump very high, and it's like that ramp, you can just jump super high. So yeah, I definitely need to just remove that. You should jump at a constant Z velocity in the positive direction. So let's go fix that real quick. So that's like jump, right? So basically our velocity Z is going to be the current velocity Z plus the sine of the direction Z times the velocity. So we need to like clamp this thing, as far as I see. So if our... And it should be... Yeah, if we're running off a hill and we start falling, that's fine. So we should actually, I think, just set our Y to the velocity here. If we just do the sine of the direction times the velocity. So our Z, no, I got it wrong. It should be Z. I keep looking over at the wall where I've got the axes all mapped out on paper every single time, and I'm like, which one is it? And that way my brain doesn't have to remember anything. It's like my brain has a little thing. It's like, oh, where is that information? Oh, it's to your right. That's where I'm storing part of my brain. On the wall. That didn't do anything. What the hell? Alright, line 678. 698. I wonder why our z velocity is so high. So info log z velocity has been set. So what is this? New velocity, wanted velocity at y. What is wanted velocity in this jump situation? Is it that our wanted velocity is incorrect at this point? Because we're just setting our velocity, and our wanted velocity is going to be Are we ever actually calling these things? We got directions and all this other crap. Alright, z velocity has been set to that, but I think when we're actually doing this, like new velocity is current velocity, and then we lerp to our wanted velocity y based on what's going on. So if we're holding up new velocity.y equals y, new velocity x equals 0. Did I screw something up? Like, we're just doing the y, so it's the z that should just be set to like our current velocity z. Because we're not using our wanted velocity z whatsoever for locomotion in the air. So we're gonna do like info log the current velocity in z is. Because why is that getting set? Like, we are setting it to a specific value. Why is it getting set differently? Did I just compile after, or compile before I wrote it, or save it, and that got messed up? So I didn't actually build the code, or is something else changing the current velocity? Like we're running another update loop or something, and all of a sudden we're updating in the wrong order. Why did we put an S there? Because we were trying to save, and Visual Studio is slower than us, probably. It's actually not very warm in here. It's too cold in this basement. Maybe it's because I'm drinking cold water and cold caffeine. Maybe? Probably. So let's take a look at our velocity as it changes. So our velocity has been set to 6,000, and the current velocity z is 6,000. Alright, so a normal jump is like that, just boom, that works. For running up a ramp, our normal jump Alright, it looks like our code did work. We just didn't compile it, so we just kind of wasted some time when we already had it fixed. That's fine though. Good, everything works. It's like, that totally should have done exactly what I wanted. The cold breath of the dead? Oh god, the undead have followed me from Battle Brothers in the frickin' Visual Studio. Son of a bitch. I'm gonna go get a sweater. Yeah, so all the mercenaries that ever died under my command are haunting me. There's a lot of them. There's a lot of them who've died. And some of them have died multiple times. That's just kind of what happens when you put me in charge. So let's take a look at exactly what's going on here with this function that we're dealing with. So we kind of figure out a start position for our locomotion in the air. We then do like a sweep in the direction of motion, and then we figure out if we can land, and then we apply wall friction, and then we do all the things. Should you be concerned about Adam? He'll be fine. Oh yeah, he'll be no problem. He'll be nothing bad will happen to Adam. Nothing bad at all. Well, we could probably combine some of this, but I'm not convinced. Because there is actually a difference in what this logic is doing, because this logic has to do a lot more random crap. So I think we're not going to try to combine that logic. It's just something that we're not going to do. So, variable jump height based on holding the jump button. So how should we implement that? So, if you hit the jump button, we want you to jump kind of until you're holding it. So I should probably... Alright, so... let's think. We would like to kind of do Mario style jump, right? Where if you hold the jump button for longer, your guy will actually keep moving up. Let me just pull up a video real quick. You're charged with keeping him alive? Well, then we may become mortal enemies. Because I am charged with getting Dashkin finished, and if those two goals are at odds with each other. So let's see. If Mario's moonwalking around and jumping, yeah, does he immediately stop? Yeah, he kinda has this constant velocity, doesn't he? What? Kinda reaches an apex and then. Well, Mario's jump is totally different, but I'm just looking at kind of the air control. And it's definitely like with Mario, I'm pretty sure they hard coded every single frame of the jump. Like that was just a thing they did. What the fuck? Alright, so what we're gonna try out is basically we're gonna have an intent to jump sort of thing going on. Where what you can do is call keep jumping or something like that, like set keep jumping. True and false. So I guess it's gonna be like set. Because as soon as you like stop holding the jump button, I want your positive Y, your positive Z velocity to go to 0 very quickly. So all we should say is what would you call that? Because I'm searching for a good. So like void set kill jump velocity, and I want that to like bool kill jump. So it's really just the opposite. We're actually wanting to kill the jump, and by default we don't. So because like if we're writing an AI script or something and just says like okay jump, mortal enemies, bring it on. Oh no. So if kill jump is true, then we're gonna do stuff. But basically, when this thing should be false to begin with. So if like an enemy script does something, when you call jump, it just gets reset. So like kill jump equals false. It's just always gonna do that. And should we have like a minimum kill jump time, or should we have like a kill jump decreaser speed? Yeah, I think like a kill jump decrease thing. It's gonna be a float. It'd be like G kill jump constant. What's gravity right now? Gravity is at like 10,000. Let's throw it at like 30,000. If we go to our CC right here, basically what we can do is we can say if virtual controller is key pressed, the E action, A action. So basically if the A key is not pressed, then we're going to call our movement and we're going to say set kill jump to true. So what happens here is when you hit the A key, triggered, so the triggered happens only on the first frame when you press a button. So it's going to jump. That's going to say kill jump to false. And as soon as you let go of that button, set kill jump is going to be false. I mean, set kill jump is true, and you'll slow down really, really quick. And we don't want you to unkill your jump. So, like, if you press the button and then you let it go and you press it again real quick, we don't want you to keep going up. We want you to, that first kill jump, to actually kill the jump. So that's what we're doing with that. Set kill jump is what we want. Because what we're going to do here is we should probably be like instead of doing is key triggered with the jump button, it'd be like, well, are you in the air or like already jumping, and like we need to reset this so it's like is key pressed. So if you like trigger the button a frame before you hit the ground, you'll actually like on the frame you hit the ground immediately jump. Right now you have to actually press the key after you're on the ground, otherwise like you hit the key of the frame before, the next frame you land, you're not going to jump. So we have to do like if you're in the air and blah blah blah, some basic things. So kill jump, we need to apply this at the beginning of update locomotion in air. So basically we are gravity velocity is plus equals there. So we're going to have our F vector kill jump velocity. No. So we're going to say if new velocity dot y is greater than 0 and m kill jump, then new velocity dot y minus equals kill jump constant times delta t. And if new velocity dot y is less than 0, then new velocity dot y equals 0. And we're applying this after gravity because, I don't know, it might make a difference. Like, on the frame you let go, it's not going to immediately make you go flat. Like, if you were right at the top of your jump, it's not going to make you immediately go down. It's going to make you kind of stop in the Y. And that might make a difference. I don't think it really would. You might not be able to notice it, but it might if somebody was like frame perfect jump or something like that. This would make it so the frame perfect jump would be easier to make versus like using subframes or something like that. I don't know if that terminology makes any sense to most people. But since we're doing like sub-steps and stuff like that, it wouldn't be just a frame perfect trick, it would be like a sub-frame perfect trick, which would mean it's kind of out of your control. Because like the previous frame rate would have to be exactly as you wanted it to be, so that this sub-step got you exactly where you should be and all this other bullshit. Because the physics step runs, yeah, subframes, because the physics runs at a different frame rate than the game. Basically how the physics runs is we run it in constant time. If you didn't see my explanation earlier or all that, basically what happens with physics with games is you're simulating stuff basically like, so if you got to jump, in the real world a jump looks like you jump up and then you come down, right? So it's like a perfect parabolic arc. So if you're trying to jump up onto like a platform, you know, boom, I can land on the platform. But in the game world, like if we've got a platform that we're jumping on, if you jump, it's more simulating it like we're gonna have like this jump velocity up, and then you know we've got a velocity to the right as well, and we apply gravity. So what you do is you add all those vectors together for each frame. So if you're simulating for, you know, like a second here, you're basically saying, okay, he's gonna go up here for a second. We're gonna, you know, add the gravity in there, and we're also gonna move him over here. So the character's movement actually looks like this on the frame. And then again, you would take this position next frame, you would move it up, you'd move it down, and then you move to the right, and you'd end up over here, and then over here. And these steps right here are, each one of these steps is a quantum in time. And if you have a really high frame rate, you're actually going to have a higher arc. Yeah. So you'd have like a higher arc because each one of these slices, is at a different time. So it's calculus, right? Like if the slope is, if you use an infinite number of time slices, you're going to get that perfect parabolic arc. But if you use crappy, you know, what computers have to do, because you can only simulate so much time. If you slice it up, your jump is always going to be, this approximated jump, which is not perfect. So you could either calculate, you'd get like your jumping point, you take your time in the air, and then you calculate where you should be based on the jump point and all that sort of stuff. And that would allow you to always just calculate, it's been 17 milliseconds, the point in the arc I should be at is right here. So you can do a perfect arc jump. The problem with that is you have to know all the information along the jump and apply everything from the start. So like if you were doing your jump, right, and you hit like a frickin' wall while you're doing the jump, like how the hell do you calculate nicely? You'd say like, okay, well I left the ground at this time, so I should be, at this height in this component, but I ran into the wall, so I should be, here or whatever. And so calculating it perfectly is a real pain in the ass. So what you do instead is you just say we will always advance in equal increments. So while this is going to look, our arc is going to look jagged with what it does, it's always going to be the same. So if I'm running at 120 FPS or 60 FPS or 30 FPS, I'm still always going to make the jump. Versus like old school games, you'll see a lot of first-person shooters where you don't, your friend has absolutely no problem jumping up into the secret tunnel in Mario Kart, but you can't, and you never can on your machine or something. And well, that might be because they're running at a higher frame rate than you, and that can have a big impact on physics in games. So we break it up into steps, and we basically say 5 millisecond steps is what we're doing, and 5 milliseconds and a little bit extra. So if we're 17 milliseconds in a 60 FPS game, we'll simulate 4 times, 3 times at 5 milliseconds, and then once at 2. Which is exactly what's going on. So hopefully that explains what I'm attempting to do. Yeah, so when I talk about subframes, I'm actually talking about those sub-physics steps. Because when people are trying to do like frame-perfect jumps and crazy stuff like that, if the motion they're always going for needs to happen within that 5 millisecond frame step time, then they have like, a 1 in 4 shot of making that jump. If they hit the right frame with it, they'll have a 1 in 4 shot of like missing, because the physics step that they took when they expected it to be 5 milliseconds was 3 or 2 or something. Then they might, if it's a very perfect situation like in Mega Man X where you're trying to jump up on to get the heart container when you don't have the right items, that can actually affect the jump. So you'll see like somebody that's amazing at the game will always nail it, but sometimes it's a miss regardless of what they do. So they'll have like some sort of setup that perfectly aligns it so that they'll always hit that specific platform on the first quantum of the frame on the frame perfect jump. Yeah, it's a big part of the reason why games are always so screwed up with physics is because there's just so much to think about. And if you were a new programmer to making games, you might not realize that just multiplying, your velocity by your time and adding it to your position is going to result in you not being able to make a jump sometimes because of a shitty frame rate. You'd be like, well, it works great on my machine. Alright, so that's... I'm not seeing attempt to kill jump doing anything. So kill jump is never setting to true? What is going on here? If the A action is not pressed, then set kill jump. Well, there's totally no way that this is not happening. So that's why when I'm working on this like platforming code, there's probably all sorts of crap I'm missing in that I've introduced with the decisions I've made that somebody who's worked on platformers for forever would just say like, you're an idiot, like your platformer sucks, your code is just obviously trash, you're trash, I hate everything, I hate you and two included, so have fun. So kill jump is true, new velocity.y. Oh yeah, that's because I'm an idiot and it's new velocity.z. It's .z. There we are. Jumps out the window. Yeah. Yeah, because you look at like some games like other platformers, they've implemented collision based on having a sensor around the object, and you basically collide with those. You do like an overlap test with the sensor, and based on that, you can do all sorts of things. Like it depends though. We're figuring it out, and the way I've put it together basically allows us to use sweeps and raycasts and all sorts of crazy stuff to keep ourselves out of geometry. The next step is going to be to put moving geometry in there. So like when we should not be able to collide, we should not be able to penetrate an enemy. So let's see. So that's if the jump is killed, but why is kill jump set to